Easier than it is.
But so I say that the logic of that
I don't know. These three and about to get that link. So you said it twice, and that's like 2 minutes.
So some people can't think like that. You could do that.
Are you guys ready? Focus on me, please. So, as I mentioned yesterday, Mr. Treater, you stop doing your math homework. As I mentioned yesterday, we have 2 fundamental properties of matter. Okay. One is mass. Okay. We measure mass in grams or kilograms. Yes. And we use the letter M to represent mass. We don't know where mass comes from. Okay. We don't know where mass comes from. We don't really understand it, but we know it's a fundamental property of matter, which in itself is fine, because sometimes when it comes to physical laws or physical properties of the universe, we don't know why. Like gravity, for example. Like, why gravity? I don't know. There are some hypotheses about it, but none of us really have a good sense of where gravity as a concept comes from. That's okay. We don't need to know. But we can do some measurements and make some predictions, and we're happy with that. So this gives rise to a fundamental force, G, M1, M2, all over G squared, where this refers to 2 masses, M1 and M2, separated by some distance D. Is that cool? So any 2 objects with mass will pull on each other. We're happy with that. The other fundamental property of matter is what we call charge. The other fundamental property is called charge. We use the letter Q, or sometimes big Q, in an attempt to confuse you. We use a capital letter C as the unit. That is a coulomb, C-O-U-L-O-M-B. That's named after somebody, but I'm not that into the history, like Bob Coulomb or somebody. I don't really have any idea. It could be like Peter Coulomb or something. Charles Coulomb. I don't know. I don't know what his name was. Okay. But what we know is that what we saw through our little experiments and demonstrations is that if you have 2 charged objects, okay, 2 charged objects, will they exert a force on each other? They will, right? So tell me about these 2. Does that look like 2 eyes and like a mustache?
Yeah.
Is that what that looks like?
Yeah.
That's what it looks like. I was like, why is that guy looking at you? If you have 2 charges, right, we're going to call this one Q1. We'll call this one over here Q2. Will those pull on each other or push on each other? What are these 2 doing? Yeah, these 2 are obviously pulling on each other. What's our rule? Opposites attract, right? So, here's the question. Can you figure out some things about this that might change the force between them? Can you figure out, can you suggest some things about these that might, what are some factors about this setup that you could change that might affect the force between them?
Distance.
Factors that might affect it. 1, distance. 2, what's that?
Mass.
Well, actually, I like that as an idea. My question is, do you think the mass affects this electric force between them?
Oh, no.
Will it affect the gravitational force?
No.
What do you think affects the electric force between them?
Charge.
We got the charge, right? So maybe Q1, and what about Q2? Yes?
Should it be the change in charge?
The difference in charge?
Yes.
Well, it would be hard to know because, like, if you change this one, the difference would change. Does that make sense? So let's do it this way and see what happens. Okay, you guys good with this? So what you guys are going to do is you're going to use, okay, you're going to use a simulation and you're going to do this. So this is going to be Q1, Q2, distance. This is the force, electric force, electric force, electric force. Is that cool? Does this setup look vaguely familiar to something you may have done recently?
Yeah.
Okay? So this is what we're going to do. So here's the simulation we're going to use today. The fancy website that we use doesn't have this, and I just every year I email like, could you please just create this? Because it'd be so much easier if you did. But I found one that may work for us. Okay? I found one that may work. I can't wait to see. Because I never used it before for this. So we're going to just jump right in and hope for the best. Which, again, that's not an issue for me. I'm okay trying and see if it works. If it doesn't, we'll do something else. We'll try, and nerds try and see if it works. We'll go from there. What? Something on my face?
Yes.
Did I just mark myself with that whiteboard marker?
Oh, yeah.
Here?
So,
Yeah. Oh, I definitely marked myself with a whiteboard. I actually felt myself do it a couple of minutes ago, and I was like, man, I hope there's not a giant black mark on my face.
There it is.
There is. Thanks. Let's see how I did here. Oh yeah, that's a good one. That is solid. That is.
Just leave it there.
No one will notice.
No.
No one will notice.
It's a bit of an interjecting there, no.
All right.
I know it's so weird.
I canceled the recording so it doesn't see the mark anymore.
What's that?
I canceled the recording so it doesn't look good. The mark.
No.
He just turns and looks at
These are just for Mrs. Hayner.
I know.
She doesn't care.
It's just so that you can see the smartboard.
Okay, so listen. I'm going to show you. You're going to do a Google search for physics classroom,
Physics classroom.
COULOMB, Coulomb's Law. Okay?
Physics classroom.
Coulomb's Law, of course, named after Mr. Law. Open this up.
There we go.
You get this cute thing here. In the top left-hand corner here, you get this little, spread it out, and then you can do the thing. Okay? So you can do the thing. So I would move them around so that the center is at like one of the, like that little blue, you can't see because it's behind, but like a little blue vertex, right? And then you can slide the charge here, all right? And what, you have the force arrows here. What do you notice about the length of each of those two arrows?
Same.
They have to be the same length. Why? It's Newton's third law of force pairs, right? They have to pull on each other the same. Okay, they have to pull on each other the same. So if I increase the charge on this one, the arrows get bigger. If I decrease the charge, the arrows get smaller. That's consistent, right?
Now, what if
Because we think more charge should be more force. Does that make sense? But what's going to happen if I move them closer?
it increases the charge?
Well, no, the charge stays the same, but does it increase the force?
Yeah.
Oh, look.
Wow.
Oh,
You lost control.
is that cool?
Now,
Now,
what if we click the switch button?
down here,
Nice.
okay, I don't, you can have positive or negative, it doesn't matter to me. Because you're interested in the force value. So it gives it to you in Newton. So I would do some distances that make sense. Do the center to center distance. So this is like 1, 2, 3. I don't know what this is in.
Let's make it.
Units?
Yeah, this is my problem with this. I haven't used this enough to have a really good sense of what this is. I'm going to have to take some time and play with it tonight. to figure it out. But let's just make it arbitrary distance measurements. Make the long lines 1 whatevers. So right now this is 1, 2, 3. The distance between these two is 3. Does that sound okay? This is easy enough, right? You guys know what to do here, right? I don't need to explain anymore. Okay, so, oh man, the lab is a disaster back there.
Oh, well.
Could be worse.
Oh, well,
Could be like
it is.
way worse.
I'm going to give you 7. I'm going to number you guys into groups of 7. You're going to move to the lab stations. I'm going to come around and give you one of these things to be responsible for. Okay, you understand that? Here we go. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Jaleel, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, Riley, 4, 5, 6, 7, 1. Move to your station. Log on to the physics classroom.
Yeah.